We will also encounter vectors in Calculus 3. So some quantities need both a length and a direction to represent them. And these include physical quantities like velocity, displacement, and other examples of vectors are acceleration and force. And examples of scalar quantities, which only have a magnitude, are mass, temperature, distance, and speed. So these quantities do not have a direction. So we represent a vector as an arrow, which is also called a directed line segment. And this vector points in a particular direction, as per the arrow. So here we have a vector pointing from P to Q. So for example, a velocity vector points in the direction of motion of a particle at a particular time instant, and the length of this vector or magnitude, as well as its units, so for example in meters per second, gives us the instantaneous speed, or the speed at that particular time. Now two vectors are equal, such as in this case PQ and RS, if they have the same length and are parallel and point in the same direction. And a velocity vector is a vector that's tangent to a curved path, and a position vector is a vector with its initial point at the origin. So these are special types of vectors that we'll explore later. So in textbooks you'll see vectors written in boldface or with arrows on top, and this can be small or capital letters, as we've shown. A position vector, denoted R, is a vector in standard position. So its initial point is at the origin, and the vector is drawn from the origin to the terminal point. So this position vector is another way of representing these two vectors, being PQ and RS. So the position vector in this case has the same length, is parallel, and points in the same direction as these two vectors. Now generally, we specify a vector in component form by writing the coordinates of its terminal point when it's in standard position. So generally, for a vector v drawn from the origin, in 3D space, it has components v1, v2, and v3. And if the vector is specified in a 2D plane, then it'll have two components, being v1 and v2. So in this case, the vector is specified as an ordered triple, and the 2D case as an ordered pair. Now two vectors are equal if and only if their position vectors are equal. So for example, if we have another vector w with components w1, w2, and w3, then v and w are equal if v1 is equal to w1, v2 is equal to w2, and v3 is equal to w3. Now the magnitude of a vector is the length of the equivalent directed line segment representation. If we suppose this position vector was v, then this vector has components in the horizontal and vertical direction, each having a length v1 and v2. So using Pythagoras' theorem, the length of vector v, or magnitude, is equal to the square root of the sum of the squares of its components. So we have v1 squared plus v2 squared. And if the vector is specified in 3 space, so it has 3 components, then the magnitude will have an additional component squared. And a special type of vector is the zero vector, which has its components being all 0. So therefore this is the only type of vector that has a magnitude or length of 0. So it has no specified direction. We need to be familiar with some algebraic operations on vectors. So here we'll look at addition and scalar multiplication. So algebraically, if we have a vector in 3 space with the following components, and another vector w with components w1 to w3, then the sum of these vectors, v plus w, results in a vector with an ordered triple of the sum of their components. So we have v1 plus w1, v2 plus w2, and v3 plus w3. Now we can interpret this graphically. So given a vector v and w, we can put the tail of w at the head of vector v, and the resultant vector v plus w is drawn from the tail of v to the head of w. So this is the head to tail method, and we can observe a similar result using the parallelogram law. So if we put the tail of the vectors together, so we put the tail of w at the tail of v, then these two vectors form a parallelogram. And the resultant vector is the diagonal of the parallelogram. Now with scalar multiplication, we can multiply the vector v by a real number s. So as we can see in this case, the scalar multiplication stretches the vector v in the same direction, given that s is greater than 1. And if s is between 0 and 1, then that'll effectively compress this vector. So you end up with a shorter vector that points in the same direction. And if s is equal to 0, we end up with the 0 vector. So you'll have 0 by the vector v, which will 0 out its components, and you end up with the 0 vector. And if s is equal to negative 1, we end up with a vector that has the same length, but points in the opposite direction. And if s is equal to 1, for example, then you end up with the same vector. So we have 1 by v is v, because you're just multiplying the components by 1. Now the magnitude or length of the vector that results from multiplying v by a scalar is equal to the square root of s multiplied by the first component squared plus s by the second component squared plus the scalar by the third component squared. And now if we factor out s squared and take it outside the square root, we end up with the absolute value of the scalar by the square root of the sum of the components of the vector squared, which is effectively the magnitude of the vector v. So note that we took the absolute value of s because the magnitude is positive and greater than 0. Given 3 vectors, being v, w, and x, and 2 scalars s and t, then we have the following vector properties And we'll first look at the properties of vector addition. So first is the commutative property. So if we add two vectors v and w, then that's the same as adding w and v. So it's similar to real numbers. And the associative property is when we add two vectors, being v and w, and add this to a third vector, then that's the same as adding a vector v to the sum of vectors w and x. And if we add the 0 vector to a vector v, then we get back the vector v. And now we'll look at some properties of scalar multiplication. So if we multiply a number 0 by a vector, then that gives the 0 vector. And if we multiply the scalar 1 by a vector, then that gives back the vector. And scalar multiplication of vectors is also associative. So if we multiply a scalar s by the product of a scalar and a vector v, then it's the same as multiplying the two scalars and multiplying the result by the vector. And now we'll look at some properties of both vector addition and scalar multiplication, so we combine the two together. So if we add a vector to another vector that's negated or multiplied by the scalar -1, then that gives the 0 vector. And if we multiply a scalar by the sum of two vectors, then we can distribute the scalar over the addition of the vectors. So we have the scalar by the vector v plus the scalar by the vector w. And the other distributive property is if we add two scalars together and multiply the result by the vector v, then that's the same as multiplying the scalar s by the vector v and adding the scalar t by the vector v. Subtracting two vectors, so for example, v minus w, can be done using vector addition and scalar multiplication. So what we can do is rewrite this as the vector v plus the negated vector w. So recall that negating a vector is just flipping the direction, and the result is an anti-parallel vector to the vector w. And then using the head-to-tail method or the parallelogram method of vector addition, we have the head of vector v on the tail of vector minus w. So we just connect a vector from the tail of vector v to the head of vector minus w, and that's the resultant vector. Now vector subtraction is not commutative, so for example, w minus v is equal to w plus minus v. So what we'll do first is negate vector v, so it looks something like this, being anti-parallel to the original vector and having the same length. And then we'll use the head-to-tail method of vector addition to add minus v to w. So in this case, we have the head of minus v on the tail of w, so our resultant vector will look something like this. So as we can see, the resultant vectors in both cases have the same magnitude, but point in the opposite direction. So these two subtractions are not equal. and therefore vector subtraction is not commutative. Unit vectors, which would typically denote with a hat, have a magnitude or length of 1. And the standard unit vectors, being I, j, k in the Cartesian coordinate system, is I hat, which has a component along the x direction, and the other components are both 0. And the vector j hat has a component in the y direction, with the other components being 0. And the unit vector k is the third standard unit vector, which has a component of 1 in the z direction, and the other components are 0. So as we can see, the magnitude of these vectors is 1. And generally, we can write any vector v as a linear combination of the standard basis vectors. So we have the first component in the x direction, plus a second component in the y direction, plus a third component in the z direction. So for example, if we take a walk of 1 unit plus another unit along the x-axis, and we walk 3 units along the y-axis, so we have something like this, and we walk 4 units in the z direction, so we have 1, 2, 3 and 4, then our vector v would look something like this. So we have v1 is 2, v2 is 3, and v3 is 4. Now we can normalize any vector apart from the 0 vector. So to normalize the vector v, we divide each component by the magnitude. So that gives us a unit vector with length 1. And this unit vector with length 1 has the same direction as our original vector v. The dot product, which is called the scalar or inner product between two vectors v and w, which is denoted v dot w, where the vector v has the components v1, v2 and v3, and the vector w has the components w1, w2, w3, is defined as the sum of the products of the individual components. So we have v1 w1 plus v2 by w2 plus v3 by w3. And this can be proven using the law of cosines, and also applies to 2D vectors. So with the dot product between 2D vectors, we don't have this third term. Now the dot product is also defined as the product of the magnitudes of both vectors by the cosine of the angle between them, where the angle between the vectors is between 0 and pi radians, or 180 degrees. So in other words, if the dot product is larger than 0, then theta is between 0 and 90 degrees. So that means the two vectors point in the same direction. Now if the dot product between the vectors evaluates to 0, then theta is equal to pi on 2. So effectively the two vectors would be orthogonal. And if the dot product is smaller than 0, then theta is between pi on 2 and pi radians. or the angle between the two vectors is obtuse. And therefore, using this relationship, so we divide through by the magnitude and take the arc cosine, and we end up with theta is the arc cosine of the dot product between v and w divided by the product of their magnitudes. So this gives the angle between two non-zero vectors. Let's look at some properties of the dot product. So given three vectors, v, w, and x, and a scalar s, the first property is the commutativity of the dot product. So if we take v dot w, that's the same thing as w dot v. And if we multiply a scalar by the vector v, and take the dot product with another vector w, then that's the same as multiplying w by the scalar and taking the dot product with v. And that's also the same as taking the scalar outside and multiplying it by the dot product between the two vectors. Now we can also distribute the dot product over vector addition. So we have v dot, the sum of vectors w and x, which is the same as v dot w plus v dot x. And if we take the dot product between a vector and itself, then that's the same as the squared magnitude of the vector v. And taking the dot product between a zero vector and the vector v gives the zero vector. We can use the dot product to compute the projection of a vector v on another vector w. So recall the definition of the dot product is v dot w is equal to the magnitude of v by the magnitude of w cosine theta, where theta is the angle between the vectors, and we can express v as the sum of orthogonal vectors, with one component parallel to w and the other component perpendicular to the vector w. And the parallel component, so using the following notation, being the projection of the vector v onto the vector w, we have the magnitude of v cosine theta multiplied by the unit vector in the direction of w. So that's this component over here. So if we substitute for v cosine theta, then that's equal to v dot w on the magnitude of w. And the unit vector in the direction of w is w on the magnitude of w. So simplifying this, we get v dot w on the squared magnitude of w multiplied by w. So this is the orthogonal projection of v onto w. So v cosine theta is the scalar component of v in the direction of w. And we can also get the perpendicular component by subtracting the parallel component from v. So if we rearrange this equation, we get V perpendicular is V minus a projection of V onto W, which is this formula here. We can also multiply vectors using the vector cross product, which, unlike the dot product, results in a vector. So the cross product between two vectors is defined as the product of their magnitudes by the sine of the angle between them. And the resulting vector points in a direction that's normal to the plane of both vectors. So if we visualize this as a right triangle, then this length over here is the magnitude of W sine theta, which is the height of the parallelogram. So multiplying this height by the base of the parallelogram, which is the magnitude of V, gives the area of the parallelogram. And this is the resultant vector V cross W, which is perpendicular to the plane of the parallelogram and points in the same direction as n hat, being the unit vector. Now the cross product between V and W results in a zero vector if and only if both vectors are parallel. So V is parallel to W, or either vector is the zero vector. So if V is a zero vector, or W is a zero vector, meaning the area of the parallelogram will be 0 in these cases. Now we can evaluate the cross product using the right hand rule. So for example, if we want to evaluate the cross product between the unit vector k and the unit vector I, then we take our right hand and curl our fingers from k to I, and then your thumb points in a direction of the resultant vector, in this case being j. And similarly, if you place your right hand in the plane of vectors I and j and curl your fingers from I to j, then your thumb points in the k direction. So I cross j is equal to k. And similarly, if we take the cross product between the unit vectors j and k, using the right hand rule, your thumb will point in a direction of I. So if you take the cross product of these vectors in reverse, so j cross I for example, then you'll curl your fingers from j to I, and your thumb will point downwards in the direction of minus k. So the cross product is not commutative. So note the cross product between the unit vector and itself results in a zero vector. And the same applies to the other unit vectors, because we have I being parallel to itself. So noting the magnitude of the cross product, which is this term, while taking the absolute value of sine theta, as sine theta can be negative, then we can find the area of a triangle by effectively multiplying this expression by a half. So the area of the triangle is 1/2 the area of the parallelogram. We can evaluate the cross product between two vectors v and w in determinant form. So what we do is take the determinant with the unit vectors in the first row and the components of vector v in the second row and the components of vector w in the third row. So blocking out the first column, we effectively multiply I by the determinant of the minor matrix containing v2, v3 and w2, w3. and then minus j by the determinant of the minor. So we block out j and take the determinant of the minor with entries v1, v3, w1 and w3, and plus k by the determinant of the minor having entries v1, v2, and w1, w2 in the other columns. So what that'll give us is v2 by w3 minus v3 by w2, which is the first component of the resultant vector, minus v1 w3 minus v3 w1, which is the j component, and plus v1 by w2 minus v2 by w1. So that's the k component. And that's an easy way we can evaluate the cross product using the determinant form of a matrix. Let's look at some properties of the cross product given three vectors v, w and x and two scalars s and t. So the cross product is not commutative, meaning that v cross w is not the same as w cross v, but it's actually equal to the negative of w cross v. So both resultant vectors have the same magnitude, but point in the opposite direction. And the cross product is distributive over vector addition. So v cross w plus x is equal to v cross w plus v cross x. And similarly, if we add two vectors v and w and take the cross product between the resultant and another vector x, then we end up with v cross x plus w cross x. And if we take the product of a scalar with the vector v and cross this vector with another vector resulting from the scalar t multiplied by w, then we can take both scalars outside the cross product. So we take the product of the scalars and multiply that by the cross product between the two vectors. And taking the cross product between a zero vector and another vector results in a zero vector. And the cross product between a vector and itself is the zero vector, given that the vector is parallel to itself. And this also applies if the vector v is parallel to another vector w. So the cross product between parallel vectors is 0. And finally, we have another identity that results from taking the cross product between a vector v and a resultant vector resulting from w cross x. So that gives v dot x multiplied by w minus v dot w multiplied by x. The scalar triple product between three vectors. So for example, we have v cross w, and we take the dot product between a resultant vector and another vector x. So this results in a scalar, which using the definition of the dot product is the magnitude of v cross w by the magnitude of x by cosine of the angle between both vectors. So taking the absolute value of cosine theta, this result gives the volume of a parallelepiped, which looks like a skewed cube. So if we take the cross product between V and W, that gives the area of this base parallelogram, and x cosine theta results from the orthogonal projection of x onto this vector V cross W. So this distance here gives the height of the parallelepiped. So we have the base multiplied by the height gives the volume. In the case where we take the absolute value of cosine theta, because the volume is positive. Now similarly, if we use a different base planes of the parallelepiped, then we can take the cross product between W and X, which gives the area of this parallelogram, and taking the dot product with the vector V gives the volume of the same parallelepiped. So these two expressions are equivalent. And similarly, if we take the plane formed by X and V, we can take the cross product between X and V and take the dot product between the resultant vector and the vector W, and that'll also give the same volume. So noting the commutativity of the dot product, this second expression is equal to the dot product between V and the cross product between W and X. So therefore from this relationship, V dot W cross X is also equal to V cross W dot X. The scalar triple product between the vectors V, W, and X, well, we take the cross product first, as we can't take the cross product between a vector and a scalar, can be evaluated using the determinant. So if we take the determinant of a matrix with the components of V in the first row, W in the second row, and X in the third row, then we have V1 by the determinant of the minor that's obtained by blocking out row 1 and column 1. So we have W2 by X3 minus W3 X2 and minus V2 by the determinant of the minor matrix that results from blocking out row 1 and column 2. So we have W1 X3 minus W3 X1 and plus V3 by the determinant of the minor that results from blocking out row 1 and column 3. So we have W1 X2 minus W2 X1. Given the two vectors, find the components of the resultant vector that results from multiplying the vector V by 2 and adding the vector W. So this is part A. So what we have is 2 by the vector V, which is 2i minus 3j, plus the vector W being 3i plus j. So therefore, we have 4i minus 6j plus 3i plus j, which is 7i minus 5j. So that's our resultant vector. And now to normalize this resultant vector, we find the magnitude, which is the square root of the first component squared plus a second component squared. So that gives root 74. And therefore the unit vector is equal to x on the magnitude of x, which is 7 on root 74i minus 5 on root 74j. And you can verify that the magnitude of this vector is equal to 1, which I'll leave for you as an exercise. Find the projection of vector v onto w, which we can write as the projection of v onto w, and the scalar component of the projection. So to project v onto w, we derive the formula being the dot product of v and w on the squared magnitude of w in the direction of w. So v dot w is obtained by multiplying the components of the two vectors and summing them together. So we have 2 by 3 minus 3 by 1 minus 3 by minus 2. So we have 6 minus 3 is 3, plus 6 is 9. And the squared magnitude of w is simply the sum of the squares of its components. So we have 3 squared plus 1 squared plus negative 2 squared, which is equal to 14. So therefore, we have 9 on 14 multiplied by the vector w, which is 3i plus j minus 2k. Find the cross product of the given vectors v and w. So we can evaluate the cross product using the determinant of a matrix, with the first row having the standard unit vectors, and the second row has the components of the first vector, being 2, minus 3 and 1, and the third row has the components of the second vector involved in the cross product. So we have 3, 1 and minus 2. So the first component of the resultant vector has I multiplied by the determinant of the minor matrix with the following entries. So we have minus 3 by minus 2, minus 1 by 1. And our next component is the unit vector j multiplied by the determinant of the minor matrix with these entries, which are not in the column of j. So we have 2 by negative 2, minus 1 by 3. And our final component is the unit vector k multiplied by the determinant of the minor matrix containing entries that are not in the column of k. So we have 2 by 1 minus negative 3 by 3. So therefore, the resultant vector is equal to 6 minus 1, which is 5i. And then we have minus 4 minus 3 is negative 7, and minus negative 7 is positive 7. And we have 2 minus negative 3 by 3, which is 2 plus 9, or 11 multiplied by the unit vector k. And you can verify that this is the correct answer by taking the dot product of the vector v with this resultant vector and the dot product of vector w with the resultant vector. And it should evaluate to 0, because these two vectors should be orthogonal to the resultant vector obtained from their cross product.